Hello and welcome. In this video, we're going to talk about properties of the Riemann integral. So we've seen how we take, just to recap, of course, we see how we take the symbol, the integral from a to b of f of x dx, and we're equating it to this operation of summing all these areas of rectangles like so. Okay, we know if f of x is continuous, or at least what we call piecewise continuous, on a to b, and piecewise continuous, all this means is that there may be finitely many jump discontinuities somewhere in there, but as long as there's just only a few of them, we can kind of break the thing up essentially, and then this integral is defined. In fact, we can go ahead and use this formula, and no matter how we slice up the interval into different partitions, as long as we keep partitioning, adding in narrower and finer partitions, this sum is guaranteed to approach a certain value, and that value will be defined as this integral value. Okay, so with that said, what I want to do now is just explore some more properties, and a few things I want to talk about are, of course, if we know things about f of x or whatever we are integrating, what can we say about the integral value that we're actually coming up with? What is this? Are there, estimates we can make and things like that? So the first thing I want to talk about, and really what we're going to do is just be listing off a set of these sort of basic properties. So the first fact I'm going to say is if f of x is just a constant, or a constant value on the interval a to b, then I can write it as follows. That's the integral from a to b of the function that's just c dx. And we expect this to be c times b minus a. Right, and this makes sense if we think of it graphically. If there's an a and there's the b, here's your x-axis, and we know c is this constant value, and we know that the function will just have that constant value over there. And of course the area under the curve is just going to be the base times the height. And of course that's exactly what this is. That's the base width, and that's the height. All right, so some basic geometry comes into play for that fact. Okay, so number two, the next property I'm going to talk about is, again, a fairly straightforward property. Now suppose I have two functions, f of x. I should also mention, actually, that I'm going to call this property 2 and 3, just because we'll do both of them together. I'm going to say it's plus or minus g of x dx, okay? So now there are two functions inside of our integral. We're summing them together to create a bigger function, and we're either summing them or taking the difference. It doesn't matter. The only thing we know is that we have this amazing fact which allows us to break up a more complicated expression into two potentially simpler integrals. Okay, and the reason this is useful is, either of these may be more convenient. Right, so an equal sign, of course, means that you can go both ways. And typically, though, I think I would frame the meaning of this identity as if you're integrating over a complicated expression involving a sum of two functions or a difference of two functions. You could break it down into two potentially simpler integrals to compute. And so that is, of course, a wonderful sort of divide and conquer type identity that can really help you simplify your work. Okay. All right, let's go talk about another one. I'll move to the next page. So now let's talk about 4. All right, so now let's say, we're going to take c is just going to be some constant. All right, well then we have the integral from a to b, and now let's say I take c and I multiply it by whatever function I want to integrate. Well, it turns out, of course, I can take c outside the integral altogether. Remember that this, of course, is a number. It's a number that we can calculate, and of course that, is just going to be, just another factor to multiply. Okay, so the idea here is if we have an integrable function and I multiply it by another number, I can take the integral of the function first and just multiply it by that number at the end, and I get the same result either way. Okay, so that's a very useful simplification that we can do to make our integral more simple. The next one I want to talk about, and this one now doesn't involve the function itself, but rather think about the interval itself. A to B. What I want to do is actually break it up into two pieces. I'll call it A to B, or sorry, I'm sorry, A to C, then C to B, right? So I have A here and B there, and let's say I put C right there, okay? So I can first integrate to there, stop, and then start again and go to there. And so we have now an identity that basically what we've done is we've broken up the integral, or the interval, into two pieces. Okay. So what I can do is say that the integral from a to b of f of x dx can now be written as the integral from a to c of f of x dx. So here, if I have some function over it, I can do this first integral and just go to there, stop, and then do another integral that basically resumes where the first integral left off, and I get the following. Integral from c to b of f of x dx. So those two integrals can be computed separately and then merged together to get the complete value. So again, just like we've seen before, oftentimes in math, in order to solve problems, often you try to break the problem down into smaller pieces. If it just so happens that breaking your integral into smaller intervals at which you're integrating over, that can often help make things a little bit simpler. Okay. The next one I'll talk about is we talk about integrating from A to B. We often use that language of A to B as if there's some sort of direction involved. And in fact, the sum, of course, that Riemann sum that we talked about, there's no actual direction involved. You can add up those areas of all those little rectangles in any order you like. But we're clearly invoking the idea of a direction, that we start at A and move up to B as we summate things, even though it's not explicit in the idea. But the idea here is that what we're going to actually admit is that delta x can be negative. We can allow integration from b to a. And what we do is we interpret that as basically saying that the delta x is then going to switch to a negative delta x. And the dx, that differential, that infinitesimally small interval, will just be switched to negative dx, right? So to clarify what we're saying here, as I'm saying is, if I take the integral from a to b of f of x dx, I can rewrite it as the negative of the integral from b to a of f of x dx. Likewise, we can reverse this around. The negative integral from a to b f of x dx is equal to the integral b to a of f of x dx. All right. So both of those statements are, of course, they are identical statements and they're both true, but this allows, again, this notion of the idea that we actually have an orientation to the area under the curve. So this orientation, of course, gets expressed as a sign, positive or negative, okay? And this is part and parcel to our notion of having negative signs for functions that have values underneath underneath the x-axis, for functions that have negative values. Right, so the next thing I want to talk about now is going to be number 7, rule number 7 for integrals, which is, we have a and we go to b, all right? We always say a is going to be a number that's less than b, and that's just an assumption we'll make just to keep our statements clear and understandable. All right, and then of course we have a function like that, and we take the area underneath the curve, and so on like that. All right, well, what about a to a? Well, it should be, of course, that there's no area under the curve with no interval. So let's just make that explicit. We're going to say the integral from a to a of f of x dx is equal to 0, always. Okay? And that is a property that we can use over and over and over again to simplify our work. Oftentimes this shows up, this kind of thing. Okay, cool. All right, so the next thing I want to talk about is number 8, our next fact of integrals. And this, again, goes into the notion of sign. If f of x is greater than or equal to 0, on a to b, then the integral from a to b of f of x dx is going to be greater than or equal to 0 as well. Also, the converse is true. If f of x is less than or equal to 0 on a to b, then the integral from a to b of f of x dx is less than or equal to 0. Okay. And again, this corresponds to the idea that positive areas are areas where the graph of the function is above the x-axis. So that's positive, versus if we have a function like this that's below the x-axis, that's going to give us a negative area. Okay. All right. So I think all these facts are adding up to a lot of very convenient ways to get at a very convenient ways to simplify our calculations and help break apart our calculations and often infer things about the value of an integral. So 9, this is really a takeoff of 8. If f of x now is greater than or equal to g of x, then we know that the integral of g of x dx from a to b, and I should say on a to b, okay, this will be, of course, less than or equal to the integral a to b of f of x dx, because f of x is bigger, its integral is larger as well. Okay, and that's a standard fact that I think should be fairly clear. If I have a function here, and this is g of x, and I have another function, f of x, that's larger, at least on the interval a to b, then you expect the area to be much larger as well. Okay. 10. Let's go to yet another important property. And this is now to, we want to now, the goal here is to put bounds on the integral f of x dx over a to b. Okay, to do that, what we want to do is say that, suppose we know that little m is some number that's less than or equal to f of x, and we know there's another number, big M, that's greater than or equal to f of x on a to b. All right, so we'll say that little m and big N, we'll say that they're known values, that they're sort of I'll say they're known bounds, right? They're numbers that we know are smaller and larger than what f puts out on that interval. So we can say the following: the integral a to b of little m dx, and this is really just taking our property 9. We know that that's going to be m times b minus a. In fact, that was our property 1 that we're using there. That is going to be less than or equal to the integral of a to b of f of x dx, which is then in turn going to be smaller than the integral from a to b of capital M dx, which we know is going to be m times b minus a. All right, so this is a way we can now say, maybe I don't know how to compute this integral. Maybe it's not something I know, but I do know something about what values f takes on. Well, now I have a way of at least bound. I can basically put a lower bound and then also an upper bound that tells me what the value of the integral is going to be able to take on as we, if we can say nothing more about the integral of f, we could at least say that. Okay. And we know, I hope you're getting that calculus is all about approximation. Approximation is how we start everything in calculus. We see this showing up over and over and over again. So there are 10 important facts about integrals, and we're going to use these over and over and over again in the coming lectures. And I think if you don't see them immediately, I think everyone gets very good at anticipating and using these properties over and over and over again. They become just part of your knowledge. All right, so I hope that summary of integrals is helpful for you. And again, we're going to repeat and see these over and over and over again until they become kind of hardwired into our ability to solve problems using integration. All right, thank you very much.